So my name is Louisa Stanlake, and I'm from LB Foster in Vancouver, Canada. And I'm here to tell you how you can use twin discs to evaluate the materials in the third body. So the third body really dictates the frictional behavior between the wheel and rail, but it's really hard to simulate because it's constantly changing its composition. It's once been described as the bathtub model, where you have multiple taps and multiple drains. So how can you possibly simulate all of this without having to go to the actual real wheel rail? So today I'm going to really focus on a couple of these taps and how we can use twin discs to simulate them. So the first tap is this intermittent FM tap. So this is if your railway has a friction management program. So you apply gauge face greases or friction modifiers, solid sticks, you add greases, whatever. So this is what you add into the third body, and those materials are typically added so that you can reduce wheel and rail wear, as well as looking at energy savings, noise mitigation, or mitigate corrugation development as well. The other tap I'm really going to look at is this environmental tap mixed with moisture. So the number one there is the leaf fall. So we've seen a few presentations. There's a whole session on it on Monday. I'm not really going to focus on leaf fall. What I'm going to focus on are some other environmental aspects that you might see. I'm going to touch a little bit on leaves, because how can you not? It's one of the biggest problems with low adhesion. And so these are the two twin disc machines that we have at LB Foster in Vancouver. We have the small, what we call the small twin disc rig, which is a 55 millimeter, as well as a 300 millimeter. So we are able to kind of scale it up a bit and get the 300 millimeter is capable of about 100 kilometer per hour surface speed. I did in the paper talk on some of the testing we did on the 300 millimeter test rig, but today I'm just going to focus on what we did on the 55 millimeter test rig. So I'm first going to start with introduced top-of-rail materials. So again, as I mentioned previously, these materials are typically added for noise mitigation, corrugation development, and mostly mitigating wheel and rail wear. Now, there are many different types of top-of-rail materials, and they can kind of be classified into three different classifications. There's what we traditionally know as the water-based friction modifiers. There's the water and oil-based hybrid materials, as well as the completely oil-based lubricants. And with increasing oil, you get different frictional characteristics. So you go from sort of intermediate friction to low friction, depending on how much oil is added, as well as what oil you do add. And also the drying characteristics really change. So oil doesn't dry. So as you add in oil, you're changing the drying characteristics of the product. So this makes it really hard to directly compare these materials. In fact, this is kind of the first one we've seen in published papers on how you directly compare all three of these different classifications on the twin disc. So when we look at twin discs, what can we look at on these materials? So the first one is the retentivity, or what we call retentivity, which really relates to the durability of the material. How long is it going to survive this wheel rail environment? And it also kind of relates somewhat to carry down an actual field application. We're also going to look at the friction characteristics. So it's desirable to have those positive friction characteristics for this to mitigate the stick-slip oscillations that can lead to the noise development as well as corrugations. So we really want to probably have this positive friction characteristics. Also, we want to look at sort of relative friction levels, so that maybe our customers may be concerned with traction when using these products. And also we can look at RCF propagation. So I'm not actually going to talk about RCF propagation on these materials because this has been published before, but we also were able to repeat these results with maybe some new comparisons between these materials. So this is the first one I'm showing here is more what we call the retentivity or durability test of our products, and also different friction modifiers and hybrids. So I'm testing all four of these materials, but I'm focusing first on the friction modifier B. We do a dynamic addition to the twin disc, and this really simulates the material being applied in the field a bit better than if you paint the disc prior to your test. Because in the field, the material is squirted out onto the track, and the wheel runs by and picks it up. So it's a wet addition to the material. And all of these products have different drying characteristics. So we wanted to mitigate the drying risk. The friction modifiers will dry, the oil-based products won't. By adding it dropwise right at the beginning, we negate the differences in drying characteristics. So you can see here, we start off with dry conditions on our twin disc rig, and we add the material, the friction drops, and as it's consumed, it starts back to dry conditions where we can add more material. And we can do this cyclically and do it multiple times. And what we're really looking for is the time it takes from the addition or the initial drop in friction to the time it takes to get to 0.4. And that's what we call our retentivity of the material. So you can compare all 4 of these different materials that up here, listed here. And there's a few things we can note. And the first one is this yellow line here, top rail product D. This is a completely oil-based material. These materials do have way better retentivity than the water-based or hybrid materials in history, and have shown to have better carry down in the fields. But the other ones here, you can see the differences in retentivity and also the differences in their initial friction drop. And in fact, this friction modifier here has a lower friction drop when it's initially applied to the twin disc. But we can summarize all these materials here. But of course, because of the retentivity of the oil-based material, it does kind of swamp it out. But we can blow up this region here. And we can note that A has a bit of a lower retentivity than B and C. And we did do a field trial, which we wrote in the paper, that A actually did not perform as well as B and C. So because of the time on these talks, we're just going to focus on B and C and how we did a field trial with these 2 materials. So when we do a field trial with top rail materials, we're really looking at lateral force reduction compared to not applying these materials. So the materials are applied in a wayside applicator, squirted out onto the track. The trains carry it into the curve. So the particular curve we used was over 5 kilometers away from the application site. And it's a very tight curve, so it's an 8-degree curve. And for those non-North Americans, that's about a 200-meter radius curve. So very sharp. In this curve, we have strain gauges that measure the lateral force reduction. So we initially run under baseline conditions, and we can measure the lateral forces in kips, or 1,000-pound force. And you can see these high damaging forces, about 12 to 15 kips, are really damaging to the rail. And this is what we want to mitigate with these top rail products. And so you can see the shift to the left of the material when applied at the exact same application rate, that B and C have very similar performances. So we did see on the twin disc they had similar performances, and actually in the field, even though one's a hybrid and one's a friction modifier, they still have very similar performances. And we also show this with some gauge face greases we tested. So now I want to move to how we look at the friction characteristics of these materials and how we do a creep curve. So in traditional sense, some creep curves can be done where you change the creep throughout the run. But we find because of the material's retentivity, as you increase creep, the retentivity of the material starts coming into play and the material is burned off. So it's not a true run of what the material is under different creeps. So what we do is sort of a single point creep every time. So we start off with dry contact to kind of initiate the same starting point for each run. We apply the product wet in dropwise fashion and allow it to kind of run in and equilibrate. Then we can drop to free rolling and then rise to the set point creep. And you can see here it's level. So there's no retentivity of the material coming into play at that certain creep point. And we can increase. But as you see up here, at 1.5% creep, we're starting to see it not plateau, and that's because the material is starting to burn off in that particular creep time. But we can use this and plot the level of friction at this point with the creep at which it was run. And we can show a creep curve. Now, the first thing you'll know is we did do this under dry contact in the red line here, and we don't see this characteristic negative friction. And we think that's because we're actually only at 2% creep, and we need to go up to higher to see creep saturation. But what you can see from this graph, though, is that with that oil-based lubricant, you see neutral friction. And then again, with the 2 friction modifiers, you can see positive friction characteristics. So we can really look at these materials using twin disc. So now I'm going to really switch gears into looking at how we can use the twin disc to look at environmental contaminants. So I did mention I was going to touch on a little bit of leaf fall, so here it is. In case you're interested, we use Canadian maple leaves in our test because you got to be patriotic at some point. So we start with a dry baseline, we add water, get to some sort of level, and apply leaves. And you can see here that the friction drops quite low. But we also stop water at a certain point. But you can see the friction maintains its low level for quite a bit longer. So we thought, well, how can other materials environmental contaminants really affect this area as well, and with water. So we decided to test some other materials. So you might not recognize these. Boron carbide is a component in brake pads. Zinc oxide is used in coating for corrosion-resistant rail, and kaolin clay is in dirt. So these are common things that you can see in the wheel rail environment. So we start with the dry baseline, add the material, and add water, and you can see the friction drops in sort of a low level, intermediate level, and sort of a bit of a higher level. And then we can stop water and look at how they affect after water addition. But what we did find is with materials, it really depended on the material hardness. So we tested a bunch of other materials with varying Mohs hardness, and we found that if it was above 6 in these sort of area, you get sort of a intermediate drop, or not much of a drop in friction compared to if you had a lower friction, and especially down here with Mohs less than 4, especially with the kaolin clay. So with clay-type materials, you might see a risk in low adhesion conditions. And so some of these materials may not be exactly something you see a lot of in the wheel rail, but for instance, goethite is a very common iron oxide form. So you could potentially see these, and we can look at the risks of using these or having these materials in the environment. So that's all I have. I really did rush through that. So sorry. I just wanted to summarize that we did show how twin discs can be used to look at environmental aspects as well as top rail materials. In the paper, we did show how we can look at gauge face greases as well. So field trials with gauge face greases are slightly different than top rail, but we did see the same correlation between retentivity as well as field performance. And we can use these testing methodologies. The machines are very adaptable, so we can change creep, we can change load, we can change the testing methodology itself. And also, they are kind of substantiated. So we did repeat tests that we have been previously published, and so it just shows that we can go from twin disc to twin disc around the world and also see the same results. So I want to thank you for your time, and if you have any questions.
Thank you very much.
Thank you. Sorry.